In this problem, we will be analyzing the coating process. So the process is simple. There is a paint in this small slit, and we basically pull a thin wire through this slit at a fixed velocity. So then, as this wire comes out because of the no slip boundary condition near the wire, the paint basically sticks to the wire, and that way we achieve coating of the wire. And so while we are pulling this, because of the no slip boundary condition, again there are viscosity gradients inside this small gap, and because of those gradients there is a shear stress, viscous shear stress acting on this wire. So if you want to pull it out, you'll have to apply some force so that it comes out at a fixed velocity. Now here we are given the height of the height of the channel, the width of the channel, the velocity at which we are pulling the wire, and we want to calculate F. So the assumptions used here are that the tape is much thinner than H. So how we will use that assumption is, let's zoom in on this wire. So what you will find after zooming in is that this is the top wall, this is the bottom wall, this is the tape in the middle, and since this tape and its thickness is very small compared to the channel, and this channel is of width h, uh, we can assume that the tape is exactly at the middle, and this thickness of the upper half is 1 by 2h, thickness of the lower half is 1 by 2h, and since h is very small, we can assume a linear covert flow inside the channels. So since this tape is moving at the velocity v, the fluid, which is the fluid elements which are very close to the tape, are also moving with a velocity v. However, the full fluid elements which are closer to these walls, they don't move because of the no slip boundary condition. And in a linear covert flow, the velocity profile then is linear from the wall to the tape. So the linear profile. So if let's say the upward direction is y, the horizontal direction is x, then and this velocity is u. So u can be written as a function of y, a linear function of y, such a way that okay, such that it is 0 near the tape, such that it is v near the tape and 0 near the wall. So near the tape you have y equal to 0, so u will be equal to v. Near the surface, y is equal to h by 2, so u will be equal to 0. So this is the velocity profile in the upward channel. Similarly, in the downward channel, the velocity profile will be symmetric, but because of this choice of the coordinate system, it will be y plus h by 2 divided by h by 2. So again, near the tape, y is equal to 0, so u is equal to v. Near the surface, near the wall, y is minus h by 2 now at the bottom wall, so u is 0. Now shear stress acting on the tape. So here, using our fundamental convention for the stress, so stress acting on y interface in the x direction is equal to mu times du by dy. So at the tape, tau yx, y is equal to 0. So du by dy, y equal to 0. Now from these two velocity profiles, so for the upper half, du by dy is minus 2v by h, and for the lower channel, du by dy is equal to 2v by h. So, and again, if you zoom in near the tape, what you will see is that this is the tape, this is a fluid element in the top channel, and the shear stress acting on this is like this. If the shear stress acting is positive, then positive on this face, then it is directed in z direction, and the positive shear stress on a negative surface is directed in the negative direction. And so tau yx at y equal to 0 for the top channel is basically mu, and we need to substitute this mu times minus 2v by h. So this is the shear stress on the fluid element in the top channel. So this means that the shear stress here acts in the opposite direction. So correcting for the sign, the stress acts in the negative direction here and in the positive direction here. So the stress on the top surface of the tape acts in the negative direction, which is opposite to the shear stress that acts on this fluid element. Now the shear stress on the bottom channel at y equal to 0 is mu times the velocity gradient in the bottom channel, which is 2v by h. So this is the shear stress on a fluid element in the bottom channel. Again, if we zoom in on a fluid element in the bottom channel, our coordinate system tells us that a positive shear stress will be acting in this direction, acting in the positive direction on the top surface and negative direction on the bottom surface. So this is positive, and so this shear stress acts in the positive direction, and the shear stress acting on this tape is opposite to the shear stress acting on the fluid element. So the shear stress on the bottom surface of the tape acts in the negative direction. So if you look both on the bottom surface and on the top surface of the tape, the shear stress is acting in negative direction. So we can simply add the magnitudes of these two shear stresses and we will get the total shear stress acting. So tau yx total at y equal to 0 is basically the sum of magnitude of these two, tau yx top at y equal to 0 plus tau yx bottom at y equal to 0, which is equal to 2 times mu into 2 times v by h. So total shear stress acting on the tape is 4 times mu v by h. So now if we want to find out the total force, force is nothing but tau, the shear stress multiplied by the area, and the area here is given because the length of this channel and the width w is given. So the area is just length times the width, and then the shear force acting on the tape comes out to be 4 mu v L W divided by H. So this is the expression for the shear force acting on the tape. So as you can see, if we pull the tape out at a very high velocity, we will have to apply a very high stress because of the viscous stresses on the tape, um, due to the velocity gradients and the no slip boundary condition at the surface of the tape. And this force acts in the opposite direction to the velocity v. So since we are pulling the tape in the positive direction, the force will act on it in the negative direction. And the magnitude is this.